All right, in this video, we're going to talk about discontinuities and identifying them with piecewise functions. All right, so the key thing is, I think everybody understands this concept, but it's really about making sure you understand how to show your work to prove if there is a discontinuity and which type of discontinuity, or to also prove if there is no discontinuity if we're completely continuous. So in a piecewise functions, the key thing we got to understand is that where the functions make a switch. So where I make a switch from using the top function to the bottom function is where there is a potential of a discontinuity, and it appears that that's going to be at x equals -1. So I have to really explore what happens at this value. And I got to explore three different things to identify if there is a discontinuity and which type it is. So the first thing I have to identify is actually the easiest, is what happens at -1, right? And actually, this is G, not F, so I should be using a G here. So what happens if I plug -1 into this function? Well, actually, it does not exist. Nothing happens there because the top equation is only if you're less than -1. The bottom equation is only if you're between -1 or equal to 6. So you're actually not even allowed to plug -1 in. So that's a sign right away that there is going to be discontinuity here. I just got to figure out which type it is. So now I need to do is I need to check what happens as I approach from the left side, that's using the top equation, versus what happens as I approach from the right side, that's using the bottom equation. And then to note that, I have to write that a special way. And what I note for a lot of you guys is that you're not writing it the correct way, and that's why I want to teach you this. So we're going to first investigate what happens as x approaches, and that's what this arrow is. The arrow means it's going to approach -1 from the left-hand side. That's the little negative right there. And then what happens as x approaches -1 from the right-hand side. So this is the proper notation you need. And then what we're going to answer is, where is the function going? And once again, I wrote G. Ultimately, it doesn't matter, but I'm trying to stay consistent here. This is G of x. And then the same thing down here. So I need to figure out, where is the function going as x approaches -1 from both sides? All right, so now to do this, I literally have to plug -1 in. So the left side would be using the top equation. So I'm going to plug -1 in. I'm going to come over here and do my dirty work. That's the actual work of doing this. So I get -2 times -1 plus 4. That's 2 plus 4, which is 6. So from the left-hand side, as I approach -1, I am getting closer and closer to 6. All right. And what about the right-hand side? Well, that is plugging -1 into the bottom equation. So I get -1 minus 3 inside my absolute value plus 2. -1 minus 3 is -4. The absolute value of -4 is 4. 4 plus 2 is 6. So what's happening here is that the left side and the right-hand side are coming together. They're both coming together at 6. So they are meeting up in the graph. But at -1, there's a giant gaping hole. So this is a point discontinuity. So it's a point discontinuity because these two things are matching up. So my graph is coming together on the left-hand side at 6. From the right-hand side, it's coming together at 6. But at -1 right there, if this is the x value of -1 right here, there is a giant gaping hole. So that is exactly what you should be seeing in your graph. And now this actually makes a lot of sense. And this is all the work, 1, 2, 3, that you need to show this. All right, let's practice this with a second one right here. All right, these two functions are coming together at -2. -2 is where the functions are coming together. So I need to really explore what the heck is happening at -2. And the first thing I'm going to do is actually find out what happens at -2. Well, once again, I get something that does not exist. It just doesn't exist, right? Because I'm not allowed to use the top equation because that's only if you're less than -2. I'm not allowed to use the bottom equation because that's only if you're between -2 or equal to 3. So that makes it pretty simple that there is going to be discontinuity. Now I need to use proper notation. What happens as x approaches -2 from the left? What happens as x approaches -2 from the right? And what I want to explore is what is happening to the function, right? What is happening to the function? And to do that, all I got to do is do a little bit of dirty work. That's my plug and chug. So if I'm approaching from the left, that would be from below -2. That's going to be the top function. So I'm going to plug -2 into here. And -2 plus 4 is 2. Absolute value of 2 is 2. And 2 minus 1 is 1. So the function is going towards 1. Okay, great. And what happens as I approach negative 2 from the right? That's using the bottom function. Even though I'm not allowed to plug negative 2 into either function, I have to explore what happens as I get close to those values. And that's why I am doing it. So negative 3/2 times negative 2 plus 4. That is going to be 3 plus 4. 3 plus 4 is 7. So as I approach from the right-hand side, I'm going to 7. So this is clearly going to be another discontinuity, but this is going to be a jump discontinuity. Why is it a jump discontinuity? Well, because from the left side, I'm down here at 1. From the right side, I'm up here at 7. And those are going to both be filled in dots because at negative 2, I'm nothing. I'm not even allowed to be there. So that is why it's a jump discontinuity. Again, and you can actually make the graph of this. In fact, we went over that in class. You could actually make the graph of this to see it. But, the idea is that one side is going to be at negative, or one side is going to be at 1. One side is going to be up at 7. They're not coming together, and that's what creates this jump discontinuity. All right, so let's look at one more here to finish this video off. All right, these two functions are coming together at 0, so I'm going to really explore what happens as x equals 0. The top equation is if I'm less than 0 or greater than or equal to negative 5. The bottom equation is if I'm greater than or equal to 0. So the first thing I'm going to figure out is what happens at 0, which I am allowed to do, right? I am allowed to be equal to 0. And if I'm equal to 0, I'm going to use the bottom equation. So let me do a little bit of dirty work right here. That's going to be 0 minus 2 minus 7. That is the absolute value of negative 2 minus 7. The absolute value of negative 2 is 2. So 2 minus 7 is negative 5. So at 0, I am at negative 5. Okay, so far so good, right? This is potential for maybe I'm continuous here. Maybe not, but we got to keep going. So now what I got to do is I'm going to explore what happens as I approach 0 from the left and what happens as I approach 0 from the right. And I'm going to figure out what is this function doing. All right, where is this function going as I approach 0 from the left and right? All right. Approaching 0 from the left, that's using the top equation. So that's negative 0 plus 3 squared plus 4. That's going to be 3 squared. Keep track the negative on the outside. The negative does not get squared. So that's going to be 9, but there's a negative in front of that 9. So negative 9 plus 4 is negative 5. So from the left-hand side, I'm going towards negative 5. All right. Figuring out what happens as I approach 0 from the right-hand side is using the bottom equation. So that's going to be 0 minus 2 minus 7. That's going to be the absolute value of negative 2 minus 7. That's 2 minus 7, which is negative 5. So this is an example where all three of these things check out, and they're all three the same. The only way you can officially be continuous is if all three of these are the same. At 0, we're negative 5. I'm sorry, that's a terrible check mark. At 0, we're negative 5. As we approach 0 from the left, we're at negative 5. As we approach 0 from the right, we're going to negative 5. All three are matching up. And this is the proper way that you need to prove this. So when you're on a test or a quiz and you're asked to analyze, are you continuous at this given point? You have to check all three. If all three are the same, you're continuous. If the left side and the right side are not matching up, then you have a jump discontinuity. If the left side and the right side are matching up, but at that value, like in this example here, you do not exist, well, that's a point discontinuity. All right, guys, hopefully all that makes sense to you. Hopefully it's pretty easy, but the key thing I've been noticing and kind of looking at you guys' quizzes that you've taken already is that you're not showing all the proper work to describe all this, and that is what's going to be required of you. All right, hope you understand, and good luck in the future.